In our discussion of linear regression, we've seen a number of models. We've seen simple linear regression. We've extended that to multiple linear regression, which means going from one explanatory variable to many explanatory variables. We've also extended that to include categorical variables, which are non-numeric variables, as explanatory variables. There remains the question of seeing, do these models actually work? Are they good at what they do? To understand this, let's go back and briefly review what linear regression is designed to accomplish. Recall that it has two objectives. One is to be able to predict or forecast a value of the outcome. In other words, if I give the explanatory variables, I get a prediction of the response variable. The second is to find the key drivers of the outcome variable, to say which explanatory variables are there in the model, what are their coefficients, and what happens if I change an explanatory variable. What we have seen are regression equations, and we've seen how the equations help in meeting this key driver objective. So we've seen how the coefficients capture the effect of the individual x's and their impact on y. But the other objective of seeing how well they predict in total, irrespective of which x's I am looking at, is also an important criteria for evaluation. And it will help us establish certain methods for saying that one model is better than another model, from a predictive sense as well. So we need to know how well these models are performing, and therefore we need to be clear as to what performance means and what performing well therefore means. And as we'll see, we're going to take advantage of this idea that regression models should predict well as we go deeper into evaluation metrics. So, the criteria we'll use to say that a model is performing well is to quantify how well the model predictions align with actual values, how well the model predicts. To do that, therefore, we now need metrics that associate with prediction. One intuitive way of understanding prediction is to go down the route that we looked at when we tried to estimate our model. Recall that we tried to minimize our predicted errors. And our predicted errors were represented as yi minus yi hat, where hat represented the prediction. And the natural intuitive metric that we looked at there was involving the absolute difference between these errors. Yi minus yi hat, an absolute difference. And we did not go further with this metric because the purpose in fitting was to minimize it, was to find coefficients that minimized this kind of metric. Here, we are not minimizing anything on the face of it. We are evaluating. We're simply calculating a number based on predictions that are generated from the model. In that sense, this remains an intuitive metric. This remains a metric that we can use in order to say one model is better than the other, in that its absolute or its mean absolute error is smaller. So one model is better than another model if its mean absolute error is smaller than the other. Mean absolute error. Mean because it's an average of something, absolute errors, absolute of something and errors. The other way to see it, probably better, begin with the E, take the absolute value of it, and then take the M of it, or the mean of it. That gives you your mean absolute error. And certainly, this is a criteria that is used in practice. Gives an idea of how much the model predictions deviate from actual observations, and it is on the same scale as the observations themselves. So it's relative to the range of the responses, but it is on the scale of the responses. Another way in which this relative point becomes crucial is What is a high error? So when you're predicting sales, let's say that my mean absolute error is, just to make this up, let's say 10. Is 10 high or 10 low? That depends on what the scale of the sales is. So if I'm selling in the thousands, then 10 may be a very small error. But if I'm selling in the units, then 10 may be a large error. So it's relative to the range of the responses, and we may need to fix this a little bit with a criteria that is less sensitive to the actual values, so that we can look at MAE and compare itself. So we cannot answer the question, is the MAE small? But we can still look at two models and say that one of them has a smaller mean absolute error than the other, and therefore I should prefer it in a predictive sense. So, in a good way, mean absolute error does not blow up large errors, like a square does, for example. However, this may be a penalization effect in the sense that we may want to penalize large errors. We may want to say large errors should not be there in the model. And so mean absolute error fails in that regard. Squaring things helps. Also, there are certain, shall we say, edge cases, boundary conditions where the absolute thing calculation may add to some complexities. But by and large, MAE is a well-used measure of evaluation. Particularly in the case where we're comparing multiple models and don't really care about the value of the mean absolute error, but only about which model has the lower mean absolute error. But to fix this problem, so to speak, of penalizing large errors, we can go back to the criteria that we used for fitting it and look at y minus y hat squared instead of an absolute value. This will penalize larger errors and will try to say that my model should not permit very large deviations from actual values. So now, here is the criteria. I'm squaring instead of taking absolute values, and then I'm again taking averages. But because I'm squaring, now my units of sales or units of y has squared. So for example, if I'm looking at insurance premiums as my y, and it was in dollars, yi minus y hat squared is in squared dollars. That hurts my comparisons or hurts my interpretation. So what I do is I go back to the dollar scale and take a square root. So this is now back to the scale of the y. So again, error, yi minus y hat, square it. So E is squared, mean is taken, so the 1 over n average is taken, and a root is taken. RMSE, root mean square error. This is again relative to the range of responses like absolutes are. So again, it's not unit independent. It is large or small depending on what the y is. However, it is related to the variance, so to speak, which is a statistical measure of the prediction, and therefore root mean squared error is often used instead of mean absolute error. It can, as in all evaluation metrics, be used as a pure comparison. What does that mean? Take many models, take many equations, and find which has a lower root mean squared error. Now you don't need to worry about what the value actually is, you only need to compare it. When I need to work through the situation where the actual number is important and just comparables are not enough, in other words, this becomes a difficulty. MAE and RMSE are both relative to the scale of the response, and I cannot compare models across different data and scale of response values. So for the same data set, I can compare different models. But if you've got different data sets, particularly on different scales, I now cannot compare them because my MAE and RMSE now depend on the units of measurement of the y's, which could be different. This is a rarer situation, but when this happens, conversely, when I want a measurement that doesn't depend on the scale of the response, I need to normalize it. I need to in some way cancel out the scale of the response. And what I can do is something like this. MAPE, mean absolute percentage error, not mean absolute error, but mean absolute percentage error. What that means is, instead of looking at yi minus y hat, which is what mean absolute error did, I now divide by yi. In other words, I look at the error as a proportion of the actual observation. So now I'm on the same unit scale. It's an apples to apples kind of comparison. And if I multiply by that by 100, I get a percentage error. So yi minus y hat is the error, divided by yi multiplied by 100 is the percentage error. I can take an absolute value and I can take a mean. This is indifferent to the range of the response. So this can be used to compare within the same different models in the same data set, or different models within the same problem set or problem space, which means I can say, what am I being able to predict well? So I can say I can predict price to within 10%. I can predict sales to within 15%. I can predict customer lifetime value to within 20%. I can make statements like that and then see which is more predictable than the other. I'm going to have a tougher time doing that if the responses are different using the other metrics. It does have a problem though, and you can see what that problem is. That problem is that what happens when y is negative or y is close to 0? If y is close to 0, then this percentage error will blow up. It is just an artifact of taking ratios. So do not do this if y is negative, or rather avoid doing it with y is negative. You've got to be very careful, and avoid it more explicitly if y tends to be a number very close to 0. Because when y becomes close to 0, this MAP can really blow up, and this criteria becomes very influenced by a few observations. So only when the y is some meaningful number far away from 0, within a reasonable range, where this percentage error makes sense, then one can go ahead and use it. But this discussion is intended to give you a choice of evaluation metrics. And what happens in practice is that people use multiple evaluation metrics to say which is a good model for prediction, a good model for predicting new observations. And there are some things we need to think about as we think about that, to calculate these models, not just from the data set on which the model has been taken, but from new data sets, from new values of yi that are coming in, that are now being predicted using models that we've already built. So to have in some way some kind of runtime evaluation across these evaluation metrics to say, is my model still performing well in a predictive sense? Is it still predicting new observations that are coming in well? And I can have a, shall we say, a tracking mechanism to see how well my model is doing. So, is there a way to connect this to the other objective of linear regression, which is to say that is it explaining well? Is the model explaining well using my variables? This is a little harder, but let me leave you with some context of how that can possibly be done. So one way it is done is by calculating what's called an R-square. Now here's a formula for what R-square is. 1 minus, so look at what's here. In the denominator is a measure of the variability in y. It has nothing to do with the model. In the numerator is a measure of error, yi minus y hat whole square, like before. So if a model is very good, y minus y hat whole square will be very small compared to the variability in the data. In other words, the prediction errors are small compared to the variability in y, and R square will be close to 1. R square will be close to 0 if my y minus y hat is actually capturing most of the variability in y. So my regression model is not reducing variability at all in its prediction. Variability in the prediction is the same as variability in the original data. Or more precisely, variability in the errors is same as variability in the original variables. So prediction isn't reducing variability in any way. There R square will be close to 0. So what is R square? It is the proportion of variability in the response that is explained by the predictors. and is a number that varies between 0 and 1. This criteria is used by statisticians in order to say, are the x's sort of explaining the y's, not in a predictive sense, but in an explanatory sense. It tends to increase when more explanatory variables are added, which leads to a problem all on its own. But if I'm adding more explanatory variables, I'm obviously going to get a better R-square. But should I? Should it not be the case that the extra variable should add something valuable to the model? Something that is more than just a basic increase in R-square. So it doesn't account for the value addition from the added explanatory variable. To fix this problem, there's a modification of R-square that is taken, and it's called adjusted R-square. I won't go into the details of where this formula comes from, except that to say that it adjusts for the number of variables in the model. What is the number of variables in the model? K is the number of x's that are there in the model. If there are k x's in the model, so if I've got 3 x's coming into the model, then k is going to be 3. If there are 4 x's in the model, k is 4. So this definition of R-square adjusts for the number of x's that I have. And it so happens that if my additional x is not adding significantly important explanatory power, in other words, it's not explaining any more than the variables already there, then adjusted R-square may even go down. So one criteria from an explainability perspective that statisticians often use is to say, let me pick those x's that give me my highest adjusted R-square. These have explanatory power. The rest, in the presence of it, do not. Once again, let me remind you, R-square and adjusted R-square are evaluation metrics that are directed towards the explainability of the model. In other words, how well does X explain Y, and to what extent are my X's key drivers of Y? The last true criteria are evaluating a regression model based on how well the explanatory variables are key drivers of the response variable. The first 3, MAE, RMSE, and MAPE, address how well the model is at predicting, irrespective of what the explanatory variables are. Both of these are good criteria to keep in mind when we are evaluating a regression model, because we do not know what we will intend to use the model for, to predict or to explain and find key drivers. So adjusted R-square provides a sense of which variables actually help in prediction or in explanation and which ones do not. Because we're not going to add the variable unless adjusted R-square exists and increases. If adjusted R-square decreases, we will not include it in the model. It therefore provides a balance between model fit and complexity. In other words, it balances between, does it fit well, and is it a simple enough model so that I can get good key drivers out of it.